Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and here with me,
Robert Moore?
So, Robert, this is our third episode of the second season.
Yes.
Did you?
It's cruising right along, isn't it?
It is, and you realize that it's actually quite warm outside today.
I did. Yes, I saw that, and I see it's going to keep getting warmer. 40 some odd degrees potential next week in North Dakota in January.
Should I dare say it might be the sign of the end of winter already?
Right.
You never know. This has been a really
know.
strange winter compared to the last several winters that we've had.
It's been a lot warmer, folks. I mean, we're sitting here talking about last week or the week before about negative temperatures. It should still be that way.
Yeah, I mean, we seem to talk about weather a lot on this at the beginning of every podcast, but if you lived in North Dakota like us, weather is the primary thing on your mind in the wintertime.
In the wintertime, it's a driving factor.
Yeah, for sure. Now, if you have any questions throughout our podcast, feel free to use our live chat feature and to put any comments or questions that you may have in it, and we'll stop wherever we're talking about and try to address those questions and comments. Now, we are broadcasting from the campus of the University of North Dakota here in Grand Forks, North Dakota.
Yep.
So, Robert, there's always stuff going on.
Always something going on.
And when we comment about stuff, quote unquote, we always have to make sure we have that disclaimer out there in case people don't read our description of our podcast. And that disclaimer is, Rob, do you want to do the honors today?
I guess I'll do the honors. The opinions expressed in this podcast are those of myself and Wayne and nobody else. It's not the department, it's not the school, it's not the university. So we're on our own.
Exactly. So there's lots of things to choose from when we talk about astronomy. In fact, we like to pick out the current events as it relates to physics or astronomy. And there was an interesting image that was released not that long ago, once again from the
James Webb?
Yeah, James Webb Space Telescope. We've kind of been inundated since our podcast originated a year ago.
Right.
Because we're at that perfect time where James Webb has gone up and that started its science operation. Yep. And now there's almost daily, it seems like.
There's something going on.
Yeah, some new observation.
It's wonderful.
Yeah.
It's full of stars.
Yeah. So if you know 2001, you'll get that reference. If you don't, you're like, what the heck's he talking about? But anyways, if we want to go to the first slide, we'll describe what's kind of the interesting thing that's happened recently. So the paper has been submitted. This was earlier this month, and it's related to observations taken by the James Webb Space Telescope mid-infrared imager, and the image you see is on the right. Now, what you see there is kind of almost like Saturn-looking edge-on disk or something, right? You have the round black with a white star in the very center, and then you have these arms that kind of protrude sort of in I guess you call a northwest position, and then down in the southeast kind of location.
And those, I recognize them, so those arms and everything are supporting that circular region, which is called an occluding disk.
Yeah, so that's designed to block the light of the very bright star that's at the very center of that round, where that white star has been put.
Yep.
And because if you didn't have that, the light from the star would be so bright it would swamp the much fainter light that you're trying to observe of the nearby structure that's around this star.
Mm-hmm.
Now, this star, as you read from the title, is Beta Pictoris, and it has a wonderful history because, if I remember right, back in the 1980s, if I'm not mistaken, late 80s I guess it would be, then this star was found to have, this was by Brad Smith and Richard Terrell, who were actually two major scientists that were working on the Voyager missions at the time for the imaging cameras.
Mm-hmm.
And they went off to a telescope and acquired this image of Beta Pictoris. And what they discovered was there was emission coming from a disk.
Right.
That is, there's a planetary system, including dust particles and debris and so on, a planetary nebula, or not planetary nebula, but a solar system-like nebula, I guess you would call it, right?
And
debris disk.
Yeah, debris disk, and I'll chime in to say how we usually find those is because the star heats up the disk, and then the disk re-radiates it as infrared, so it produces what we call an infrared excess. There's more infrared light than would be coming from just the star. And so that's one of the reasons why James Webb is actually perfectly positioned with its quote unquote visual range to see things like this.
Yeah, so the idea of the initial project, I think, was for Smith and Terrell to go and observe in the infrared a sample of target stars to look for signs of a solar system.
Right.
And this was on their target list.
And a forming one at that.
Yeah, and this was on their target list. And when they took an image of it, it's like I think this was the best example they have of the direct detection of light, infrared, coming off of the debris disk of a solar system that's either in the act of forming, whether it's young or old. I don't know if you can really tell. It seems like it's young because there's a lot of debris around.
Yeah, it's young.
Yeah, because that material would get cleared out, either fall towards the host star or be ejected from the system itself, right, over time.
I mean, getting back into the nitty-gritty details, a young star is very violent. It produces a lot of ultraviolet light and so forth, and that high energy type photon will push the gas and dust away. It produces a very strong solar wind.
Yeah, so it'd be like if you jumped in a time machine and went back in time nearly 4.5 billion years ago, and you looked at our solar system. We suspect that this is kind of what you would see, something like this.
That's pretty much it. Yeah, the sun had to have been surrounded by a disk like this at one time, and what we've come to find out, James Webb is one of the things it's trying to do is confirm this, but what we found out is we don't see infrared excesses after about 40 to 60 million years for the most part. So the star clears out that region really quick.
Yeah, well, that gives you then some measurement of time scale in which how long it would take these planets to form in these type of solar system.
Right.
You're looking at the orders of tens of millions of years, not billions of years.
Not billions of years like we thought back in the 70s and 80s when I was coming up.
In fact, if you think about the cratered surface of the moon, the cratered surface of Mercury, and every object really in our solar system that doesn't have an atmosphere or a way of eroding away the features, the cratered features, the impact features, that tells us that our solar system went through this period early on of what we call the heavy bombardment.
Heavy bombardment, and then later a late heavy bombardment.
And part of that process was the clearing out of all this material and that debris left over from the formation of planets.
Right. I mean, the disk like you're seeing around Beta Pic here is primarily dust and gas. So that gets cleared out real quick. The debris can linger for a little while.
Right.
As it gloms to the larger masses, of course, suck up the smaller. And things get flung out or flung into the star. And stuff like that, kind of like what Jupiter does to comets and asteroids right now.
So you can imagine that you have some star that's heating up the nearby dust. That dust loves to radiate. Once it absorbs energy, it likes to radiate in the infrared.
Right.
And that infrared emission is relatively feeble compared to the light that's coming off from the host star, of course.
Right. So you still got to block out the star.
Yeah, so we always use the analogy, it's like looking at a firefly that's perched on the edge of a searchlight.
Right.
And
you're going to miss the firefly.
Yeah, how are you going to see the firefly? Because the searchlight is so much brighter. So if you had some way of blocking out the light coming directly from the searchlights that allows you to see the much fainter light coming from the firefly, it makes it much easier to see.
Right.
And that's kind of what's happening here. Now, to understand, the significance of this, look at the distance, how far away this star is. So this star is nearly 63.5 light years away.
Right.
So in other words, traveling at the speed of light in the vacuum of space, that fast as anything can travel, it would take you, a second to get to the moon. You go around the Earth, 7 times in 1 second, right? If you could do that. Traveling at that fantastic speed, 300,000 kilometers per second, or a little over 186,000 miles per hour. Per second, sorry. It would take you 63.5 years to journey from the Earth to this star.
All right. We're not getting there tomorrow.
No, it's definitely not the closest star to our sun.
No.
I mean, that would be Proxima Centauri at about just over 4 light years.
Just over 4. Yeah.
So this is much further away than that. But yet, look at the beautiful detail you can see in that disk. That just tells you the power of the James Webb Space Telescope and its ability to resolve features at very, very distant, objects. Now, the other information you see there, which is actually in the white text there on the bottom of the image itself on the right, is spectral type. So if you're not an astronomer, you probably don't know what those characters mean. So it's an A65 star. So the 5 at the end, Roman numeral 5, means it's a main sequence star.
Right.
So it's like our sun. Our sun itself is a main sequence star. And what it really means is it's happily converting, if you like, hydrogen to helium through thermal nuclear fusion processes in the core of the star itself.
Yep.
In fact, when an object first becomes a star, this is the phase it's at, this main sequence phase. And regardless of the mass of the star, a star will spend a total of 90% of its total lifetime as a main sequence star.
Yep. And, I forgot what I was going to say. That's when the main sequence is when it starts being considered a star. Before that, it's a Herbig-Haro object or a T Tauri.
Pre-main sequence star.
Pre-main sequence.
And before that, a protostar.
Yeah, I got all kinds of names for stuff that's before the main sequence.
And the other thing, the first character here is an A. Mm-hmm. So we arrange what we call spectral classes of stars in terms of temperature. So the hottest, and I mean surface temperature in this case, the hottest of the stars are the O-type stars. Mm-hmm. The second hottest are the B-type stars. Then it's the A-type stars.
And then K.
No, then you miss one.
I missed one.
F-type stars, and then
K.
G,
then K.
and then K, then
Right.
M for the normal sequence of stars.
I've got to use the acronym to keep them in order. But
Well, you wonder, it would have been smart to say, okay, the hottest stars are the A, the next one, coolest, is a B, and then a C, and then a D. But when these stars were first cataloged, and a lot of that work was done at Harvard College Observatory, mainly by female,
what was her name?
Annie Jump Cannon.
That Jump Cannon,
yeah.
right.
But there was others. They were used as what were called later on as human computers.
Yep.
And so you basically need somebody, a human being, that can sit and analyze data, just like a computer can analyze data easily today.
They were never given credit, but they did
until
a lot
today.
Of the
Now
analysis.
we're starting to change what happened in the past. But yeah, you're right. There was like the man who was in charge of everything, which was Pickering at the time. But he wouldn't have had those results unless he had all of these workers working under him. And they were essentially all female.
Yep.
And they were probably, I didn't read in detail, but I'm sure that the cost of them, the wages was extremely small at the time.
And before
very cheap to hire.
Before 1940s, if you referred to a computer, you were talking about one of these ladies down in the basement doing the analysis. You weren't talking about a calculating machine. You were talking about a person.
Right. And so in the early days when people were gathering vast amounts of spectra, looking in detail, if you take the light from a star, spread it out in its rainbow color, and you do it at high enough resolution, you can see these spectral features, which is a signature, for example, of the composition, and also it's the temperature effect is the main one. Composition sort of a
rotational effect.
There's rotation, there's magnetic information you can get. There's a whole slew, metallicity, the metal content, which is related to composition in that sense. A whole slew of information you can get. The Doppler effects, or whether stars moving towards or away from us, and how fast, and so on and so forth. So a lot of physics, a lot of astrophysics comes from the analysis of the spectra of objects like stars.
I mean, I hear it's passed around jokingly, but I hear the statement, "Show me the spectra," a lot of times. And it's said kind of jokingly, but it's not really a joke. You want to really know something about the star, you really need the spectrum.
Well, when you're doing observations, like the first thing you do is to take an image of something, and then the second step you want to do is to capture the spectrum of that object, because that provides all of the detailed information that we need. And so this type of star then is hotter. So the arrangement was done. When they looked at spectra, they tried to classify things. So they would imagine picking up, leaves in a forest in the fall, and they're laying on the bottom as a young child. You might pick up a leaf that has a certain shape, so you put it down. Then you rummage around, you find another leaf that looks very similar to that one, the same shape. It may be larger or smaller, but it has basically the same shape. So you put that in the same class. Well, here what was done, of course, was looking at spectra. So multiple spectra is plural for spectrum. And so you would look at the spectra of stars, and you would arrange them such that these are very similar. Let's put them in one box. And these are very similar. Let's put them in a different box, and so on. And then they realized, from the physics point of view, that what you were seeing basically was a temperature sequence here.
Yep.
So then they had to rearrange everything, and they merged certain classes. So now the highest temperature star happened to be in the O class. The second highest in terms of surface temperature is in the B class. and then it's the A class, and then it's the F class, and then the G, then the K, then the M. And in recent times, especially with infrared survey, there are a couple of additional classes that we put out on the real cool side of things.
Let's see, YT. I forget what the third one is.
Yeah, so they're,
L.
I mean, yeah, those are ones that apply not only to the very low mass stars, but even things that are so low in mass, they're not really stars as we know them. They're called brown dwarfs or failed stars. These would be objects that have a mass less than about 8% of our sun's mass. So they're not hot enough in their cores to allow sustained fusion of hydrogen into helium.
Right.
But anyways, so this is an A-type star, which means that it is hotter on its surface than our own sun, which is a G-type star. It also means that its lifetime, its total lifetime as a star, and total lifetime, therefore, in the main sequence, is a lot shorter than our own sun's lifetime. Our sun's total lifetime is about 10 billion years on the main sequence. We're about 4.5 billion years into that lifespan. And an A-type, depending on exact A6, I can't remember the numbers here, but it's an order of a billion or so years as on the main sequence.
It's roughly 1.7 times as massive as our sun.
Yeah.
So, yeah.
So that means it's not going to have billions and billions and billions of years to develop a solar system, and along with that, a system of planets to potentially have life form on one of those planets and get to the point where we are here in our evolution, right?
It's got 1 billion or 2 billion years.
And that's it. And then it's done being a main sequence. So evolve off into a red giant and so on and so forth. And so things will change in that solar system in terms of the energy that a planet will receive and so on. Now, the also interesting thing about the system, it is very complex, and you can appreciate that by looking at the image on the right. There's lots of features you can see. In fact, as you see stated here under the spectral type, is this system is known nowadays to have at least a minimum of 2 planets. So beta pic B and beta pic C. And I didn't pick those things, but
and it's lowercase b and lowercase c, because
Yeah.
if it were capital B and C, that would be other stars.
other stars around that system, yeah. And the other thing is we have estimates for their masses, and that's what's given on the far right in parentheses. So beta pic B, for example, has a mass of approximately 10 times the mass of Jupiter. So the capital M with a subscript J means the mass of Jupiter. The second one is closely, almost similar in terms of mass. It's almost 12 times the mass of Jupiter. But be aware, there's a large uncertainty on these measurements, on these numbers. So
I mean, I'm looking at it, and the disk is almost edge on, so it might be transiting. But to get a true estimate of the mass, we really need it to both transit its star and have a radial velocity curve from its spectrum.
Yeah, in fact, we'll see a little bit more of that a little bit later here. But the other thing that's interesting in this system is not only are there 2 planets, but there's also parts of the disk that can be separated. There's the main disk that you see edge on, but especially if you look towards the left side of the image itself, you see a little bit tailing down. That's a secondary disk, and there's even an inner belt, as they call it, closer to the host star. So that could be made up of asteroids and so on, if you think of it that way. Now, Robert, if you go to the next slide, please. This is a way of now describing in more detail, because we have a nice view here where people have put labels on stuff so we can get an idea what we're talking about. The new thing from this JWST image is what you see as what's called the cat's tail. So this is on the right side. That's that loop or curve that you see in the distribution. Now, these names, cat's tail, you just look at, okay, make a joke. I have a cat at home. It looks like a tail standing up. It's not a cat's tail. It has nothing to do with a cat or any other feline creature. It's just a descriptive name that the authors of this paper are using to describe.
It looks like butt wiggle mode is engaged.
So it's just a name they gave the cat's tail to this feature.
Wonder Goon asks a question. Planets with that amount of mass are almost always gas giants, right? Is that not the case? The answer is we believe so. We have evidence to suggest that, but could it be possible? Maybe.
So these planets being on the order of 10 times the mass of Jupiter almost certainly are probably gas giants. So that's what we're finding out.
That's what we're finding.
Yeah. In fact, it's kind of interesting. We find gas giants, and then we find like small rocky stuff, right? And but there's really nothing around Earth's mass. Did you notice that?
I've noticed that, yeah.
Right? It's like several times that.
It's 2 to 5 times Earth mass, and then Jupiter.
Yeah, it's like there's this like sub-Neptunian type of objects, and then there's these gas giants like Jupiter.
Yeah.
But to get down into the size scales of the Earth, or Venus for that matter, it's either they're very hard to detect,
which is the case, which is
yeah,
true.
because all these observations are heavily biased. It's not like you can survey a representative volume of space and look at every single star in detail to know exactly what they have in terms of planets.
Right.
That would give us an unbiased view of what's actually out there.
Right.
I mean, clearly, you're going to detect systems that are easy to detect.
I always like putting it in terms of radio velocity, because radio velocity is the real workhorse of finding these planets. And Jupiter, for instance, on our sun affects the sun's motion, imparts a motion to it of a few meters per second. Earth, on the other hand, imparts a motion of about a few centimeters per second. So it is very difficult to notice the movement of the star due to Earth, or the dimming of its brightness due to Earth.
Yeah, but if you have the right instrumentation,
you can do it.
You can do it. So it's really the advancement of instrumentation, advancement of technology that in the future will allow us to detect even less massive planets than what we're detecting now.
Absolutely, absolutely.
And that's the push in this whole exoplanet type of research that are undergoing even today. So the interesting thing about the cat's tail is it looks weird because you'd expected a plane or a disk of objects, and that really comes from, in physics, the conservation of angular momentum.
Right.
So if you had a huge cloud of debris, let's say, that's collapsing due to gravity, and then if there's any little bit of rotation associated with that cloud, then as that cloud then gets smaller and smaller, that rotation then increases because of the conservation of angular momentum, which is just a technical term that explains why, and here's a classic example. We always use like a figure skater. It's doing what, a pirouette or whatever you call it?
Right.
Spinning around at a point, and their arms are extended. And they can make themselves rotate even faster if they draw their arms in. Yep. And that's the conservation of angular momentum. Angular momentum depends on the mass of the object that's moving. It depends on how far away that object is moving from the central point of rotation, right? So
and the distribution of that mass.
And it depends how fast that object is rotating. So if you take those things together, then angular momentum then would be the mass times the speed times the separation distance. And of course, in physics, we can look at things like speed and then associate a direction with that, and that becomes then a velocity.
Right.
What in physics we call that's now a vector quantity. So it gets a little technical here. Something that's not a vector quantity, for example, there are lots of examples, would be something that we call in physics a scalar. So that would be like if you're measuring the temperature in your room at some location, and you say, oh, I don't know, that's 75 degrees Fahrenheit, you wouldn't say that's 75 degrees Fahrenheit west. Like you add this direction. That's a meaningless statement, right?
I will argue you can do that, but now you've moved into what we call the gradient.
Yes, that's something else. Right. But it's just the temperature itself, at some random positions in the room, that's just a measurement of the temperature. There's no directional information. So that's what we refer to as scalar. That's like saying if someone called you up on your phone and you're traveling on the highway somewhere, and right away they say how fast you're going. Well, you look down at your speedometer. It reads your speed. It's a speedometer.
Yep.
Right? And you might say I'm traveling at, 60 miles per hour. And you're like, well, what's your direction? Oh, I'm traveling 60 miles per hour north. Well, with those two pieces of information, you just give me your velocity. So that's speed plus direction. So angular momentum is the same way. It's a vector quantity. It has directional information as well as a magnitude or an amount.
Right.
And that would come from the mass of the object that's moving around, let's say a perfect circle, if that's the case, the distance from the object to the center of rotation, and then the velocity, the instantaneous velocity at some moment in time would give you that directional information. You put all that together, you get angular momentum. So it's a little technical here, but we want to push the envelope. We don't want to dumb things down, to lack of a better term.
Right.
And people say, well, don't use the word dumb. Well, there's a whole series of books that you can buy in various places called
It's whatever for dummies.
Whatever the subject is for dummies. So, that's what we're saying. People who are not experts in the field, that's what we're talking about.
Yeah.
We're not talking about anything, related to their intellectual capacity or anything like that, right? So anyway, so angular momentum then needs to be conserved. And that means that if you reduce the separation of the object from the rotation point, in other words, the extent of a person who's figure skating, as they draw in their arms, the only way to keep that value of angular momentum constant would be that they need to increase their speed,
rotational speed,
their instantaneous velocity, right? And so we would expect then as a debris disk, as a debris cloud in this case collapses due to its own gravity, its self-gravity if you like, it will rotate more rapidly. And then the structure will turn into a pancake-like object. It'll collapse more at the poles and much less so at the equatorial direction of the disk.
And I will go ahead and add in, and so what sets up a secondary disk like this is the presence of a large amount of mass that's kicking in an extra bit of energy to move some of that out of the plane of that main disk.
You know, Robert, it's past lunch, but it's before supper. Yeah. So I'm thinking about food.
Okay.
So the food part of this would be, imagine you had a round ball of dough, and you want to turn that into a pizza.
Okay.
You know, one way to do it is to get it spinning, right?
Right.
If you look at these, you know, people like pizza chefs, they're spinning up this ball of dough in the air, and eventually it turns into a flattened pie-like thing, right? Mm-hmm. You know, that's the thing we think of as a pizza maker. You get to see it happening in real time, right?
Right, but it'll wobble.
Yeah, and so this is kind of like that in that sense, right? It's not strictly true, but it's
not strictly, but
yeah, analogies only go so far, right? And
right.
Then they break down. So the interesting thing is, why aren't all these features in a plane? Because we're seeing this essentially edge on. So why aren't they all collapsed to a disc-like structure where clearly what's violating this is the cat's tail? In fact, there are other stuff in that image too that you notice. Whether that's real or not, who knows?
Who knows?
Probably is real. But the cat's tail is a really well-defined structure.
Right.
Right? It's like a hook sticking out of the edge. And so what astronomers suggest is happening here is these interactions of the things that are in this debris disk, and these interactions are essentially mostly gravitational interaction, tidal forces, right, that can cause this sort of an extension. In fact, if you want to know for sure, you don't sit down with a piece of paper and a pencil and jot down equations of angular momentum and gravity and how it operates. You'd run all this stuff in a simulation.
Right.
So you'd simulate the formation of these planetary disks.
Which that simulation takes into account all those things.
Yeah, in fact, but it's just that
the computer is faster.
Yeah, so if you're not familiar with how this would work, okay, so let's trust that some of the audience listening to this podcast doesn't know how this would work in general. If they were given the task to make a simulation of a collection of particles, let's say, 10,000 particles.
Okay.
They're occupying some volume of space, and that volume is shaped like a sphere. Okay. So how would you determine how that sphere would evolve over time? And the only forces, and that's what we want to look at in physics, is what are the forces that are applied. Imagine a particle at some moment in time is completely stationary. Then you apply forces to these particles, and the only force here that you worry about is gravity. How would that structure change? So what you would do is you pick out some random particle, let's say, and you would calculate what is the force on that particle from all the other particles that's in your sphere. Now, if you have 10,000 particles, it's much easier to do. You don't have to do some gross averaging, which you would do billions of particles. Computers nowadays have the ability, you can be able to calculate that in the computer, right? You're not going to do it on a piece of paper, right?
Ooh, in-body problems.
Yeah. And so what you do is calculate what is the overall net gravitational force on some particle due to the presence of all the other particles, their locations, and their distances from you. And then imagine that they have different masses. You could put factor that in. And so you would move that one particle a little bit in response. You would step forward in time a little bit. And then so let's just focus on one particle to keep it simple. And then you would recalculate what is now the force at this new location if the particle moved at this new time. And just repeat that over and over and over again, which a computer is designed to do in terms of software or algorithms.
I was about to say, that's what computers are designed to do.
Yeah, and then you can calculate then how things would change. Imagine you kept track of all 10,000 particles. Then you could calculate how the particles change their location and their motion relative to each other over time.
Right.
And you can run the simulation over and over again at different starting sort of positions. And after running, 1,000 simulations, you could get an idea what is the average features that you see for most of those simulations.
And in fact, what do you call it? A term for that type of simulation where you run it with random starting positions and starting speeds and starting masses and everything is called a Monte Carlo scenario.
Yeah.
You just run millions of these different scenarios and see what you get.
And so you could see that for some of the simulations that reproduce this type of structure you see here with a cat's tail, that took a certain thing to happen, and those certain things then are in your simulation. You can go back and say, okay, how did this arrive? How do these particles, which now let's say they're individual, dust particles or boulders that are giving off infrared light, how do they wind up in this distribution? So as viewed from the Earth, we see it as this cattail-like structure. And you can track down where those objects come from, and it's from the gravitational tidal forces of including all of the particles in this debris disk itself.
Right.
You can get this type of structure. There's no magic involved here. It's just physics.
And like you said, you work backwards from the principles, which ones produce that type of structure. And, that tells you then something about what's needed to get it.
And what becomes interesting in all of this is when you run simulations on some problem in physics like this, and let's say 1 out of 1 billion simulations reproduce your result, all the other ones don't, then you know that that's highly significant because it has a very low probability of happening in nature, and one would think it would never happen, yet you have observations that show it exists. So that's when the very interesting physics comes out of simulations like that.
There's that Six Sigma.
Yeah, or more than that. At that
or more
point,
than
right?
that,
Yeah.
right?
So that very, very highly unusual, and therefore that's what
Right.
focus your attention. Why do we have it in this case?
The bottom line is it doesn't happen at random. It happens under these specific circumstances.
Yeah, it would be like if someone won the Powerball every draw, the same person.
What were they doing?
What's going on there, right? Because that is the probability of that happening is so low. Right?
Something's going on.
Something weird is happening that is skewing, right, the probability that goes into it. It's supposed to be totally random, right? And given the number of numbers you need, the combination, there's a very low chance, 1 in 200 million or whatever it is, of winning a given Powerball, right? By selecting random numbers.
And so to win 2 is
so if you do 2 in a row and you do 3 in a row, then 4 in a row, you probably end up in jail, and then they'll try to figure out what you did wrong, legal, right?
What you were doing illegally, yes.
Yeah. So anyways, that's how they figured that out. So it's a very interesting result from that point of view. Now, to talk a little bit more about the planets that seem to exist, we can see them, directly image them, going around this star. Robert, if you please show the next one. So on the right here, we actually have an image where the central host star has been blocked, so we can't see it. But the dot you see, and that's represented the position by that yellow star. That's not a real object. That was just put on there to tell you that if we could see the host star, this is where the center of the star would be located. Okay. But the bright sort of whitish blue object you see in the upper left, that is actually a planet. That's in orbit around this host star. In fact, you can go online where this still image was taken from and watch a movie clip as this planet dives down towards that yellow object there and passes out the other side, and you can all of a sudden it disappears because it's behind the occulting disk, and then reappears in the bottom right, and then turns around and goes back. So it's on this sort of radial type of orbits as viewed from the Earth.
And as we mentioned, the disk looks edge on, so that would be what you would expect. That's consistent. And
a sense of scale is given there too, by the way. In the very bottom right, we have 5 AU. So AU represents an astronomical unit, and it's the average distance between the Earth and the Sun. So that distance scale, that length, that segment you see there in white underneath 5 AU, that's the 5 times the distance from the Earth to the Sun on average. So you can tell that planet, the position that it's at now, is over 5 AU. It looks like almost closer to 10 AU.
Which put it about like Saturn.
Yeah, from the distance from its host star.
Yep.
So we know this system. What do we know? So let's summarize all of this. Number one, we know that this star has planets.
Right.
We know that this star has a debris disk, sort of like the early years of our solar system would look like. Number two, we know that the debris disk is not just a simple flattened disk-like structure like a pancake, that it has structure associated with it, including the one that we showed here today, the new observation being the cat's tail. So we know that there's some very high-ordered, if you like, complicated, really, in a sense, of gravitational interactions that are occurring within this debris disk itself.
Yep. And I would like to mention something given this picture. All that blue smeared out stuff, that's residuals from getting rid of the glare of the star. That is not the debris disk or something like that. That is, we modeled the light from the star so we could then subtract it out and get rid of it. And that leaves the bright dot of the planet, which would normally, if all you had was one picture, would not be taken as, hey, we got the planet. As Wayne mentioned, we've got several pictures where the thing moves as we expect for a planet.
Yeah.
And that dot moves. So these other dots just move in a random pattern from picture to picture as we model out the light of the star. But that one moves as we expect a planet to move.
Yeah, that's a good point. In fact, we have to alter the contrast of these images to the extreme to bring out that much, much fainter light of the planet itself.
Yeah.
And that's why you see a lot of those artifacts ringing around the edge of the image, is because of that huge adjustment in that contrast.
I always like using the example of Jupiter and its moons, which we've mentioned this on this season of the show, that the larger of the moons, Ganymede and Callisto of Jupiter, would actually be visible to your naked eye if Jupiter wasn't there. Jupiter, as dim as it seems, is actually bright enough to glare out Ganymede and Callisto.
Yeah. So if you see one dot like you see here, you might say, well, is that really a planet or an artifact? Well, you keep taking another image like you mentioned, and you can actually see this planet moving towards a star, out the other side, then turn around, come back again as it's orbiting the star over time. You can actually see the orbital motion of this object, and that clearly means it's got to be real, and it's a planet in this case, given what size it is.
Yeah, I mean, I like pointing out, it's not moving at random. It's moving in a prescribed way that we can model by saying, hey, is this a planet? And it moves like we expect.
Yeah, just like planets orbit our own sun, right? If you're in the right position, far away from here, look back at our solar system edge on, you'd see the same kind of thing.
I mean, I can guarantee you somebody plotted out what the motion would be, made a prediction about that, and sure enough, the planet, or the picture that we have of the planet, moved in that way.
Now, if you go back to the JWST image, you can go back to the next slide or one before that, it's fine.
Okay.
So an interesting thing will occur here is like, how unique is this type of system? And so what you want to do, of course, is to look at several other stars, and they could be one similar to this one or maybe a different type of star, right, in terms of the surface temperature. Maybe look at cooler stars or even hotter stars to see if you can resolve, the early planetary-like disk in those stars. This one we knew exists long before JWST.
Right.
It's
from
this is
one of the
ground-based
first
images.
that they noticed.
Yeah, this was the first
disk.
one, if I'm not mistaken. So there are other ones out there as well. This is not the only one. But what about ones that we haven't been able to see? And with the light sensitivity and the resolution that JWST provides, it's going to be really interesting to see what else we discover. And you never know what type of debris disks we find in solar system, right, that we actually can observe with this telescope.
I will point out another one that we spotted a long time ago and have since seen the planets moving around, kind of like the pictures we've shown here, this one, Fomalhaut.
Right.
And so I'm kind of interested in if they'll turn James Webb to Fomalhaut and see what it'll see with that.
Well, on the point of space exploration, if you want to get outside of our solar system at some point in the future, and there's talk, to do that by various means, even with nanoprobes and using, like high-powered laser light to push them towards like the nearest star to the sun,
solar
Proxima
cells,
Centauri, all that kind of stuff. You'd like to have, the first target we're going to get to is probably going to be Proxima Centauri because it's the closest star to our sun, 4.2 light years away. But you'd wonder, okay, is there any planets around that star? And there is, thankfully.
Yeah.
There are planets around Proxima Centauri. So not only is it the nearest star to our sun and therefore probably the first object we'll explore in terms of stars beyond our solar system, it also has a system of planets. So we can, explore those as well. Now, did any type of rudimentary life form on any of those planets? How do you know until you go there? You don't know, right?
Right. Well,
So-
we can taste its atmosphere using spectra,
Yeah.
but that takes an appropriate alignment of the planets with the star and us and things like that. Otherwise, you can't get a spectra of the planet. It's not giving off its own light.
And of course, with the SETI type programs, the search for extraterrestrial intelligent programs, one of the things they do is point a radio telescope to the star and then pick up maybe some signal coming from intelligent life that have radio technology that's beaming that stuff out into space. And they've done it for Proxima Centauri, and they haven't detected anything. But I mean, that goes down that rabbit hole as number one, did life advance to the point where they developed technology that would allow us to capture those signals? And number two, even if they did, how long do they use that technology before they go more advanced and no longer emit these signals out into space so we then can't detect them?
Like again, we're fading. We're starting to use technologies that don't require us to broadcast out into space. So we haven't wiped ourselves out, but we're about to be radio silent.
Yeah, well, I mean, the good example of that for our technology is go to some young person today and say, do you know what TV rabbit ears are? In fact, you could hand them, if you can buy them off of eBay or take them from a museum, you can hand a set of rabbit ears to a student.
Why did you straighten out that coat hanger?
And say, what do you think these were used for?
Right.
And they may not have any clue, right?
Right.
And so that's really the advancement of technology. When we're beaming TV signals through the air, some of that stuff can get outside of the atmosphere of the Earth through the ionosphere, if it's the right wavelength or frequency. But eventually we get to situations like we're beaming that stuff through fiber optic cable or coax cable before that.
Or a narrow beam bouncing it off of a satellite.
Yeah, and so that stuff is not leaking into space at the strength that it used to. Because of that, we're becoming more energy efficient in the way we broadcast information.
Right.
And so therefore, some civilization that looks at Earth, if you pick the wrong time, you're not going to hear, Hello Lucy or whatever those shows were that they talked about, right? The broadcast of the Olympics in the 30s from Germany at the time, if you think of the movie Contact, right? That stuff is no longer being broadcast out there. The only thing that really is, as far as I understand, is like some of the military radar and aviation radar is pretty strong, and that gets out into space that some other life form may detect.
And I think SETI and a few others have tried beaming signals out, haven't they?
That's been very rare. I mean, way back in the 70s, there was a beam to a globular cluster, M13, that was purposely done using a radio telescope, Arecibo, in fact, which no longer exists, unfortunately. That collapsed a couple of years back. And it was a big radio dish about, 300 meters across in Arecibo in Puerto Rico. But there's been other people have done it on their own. And there's been some talk that we should never do that without the UN giving their permission. Because you may be letting other civilizations know, hey, we're here.
Right.
And because we beamed a signal purposely towards some star system. And maybe it's the Borg. So they'll have to come here and assimilate all of us, right?
And I always point this out, how much intelligence does it take to sneak up on grass?
Right.
So, what happens when you put two carnivores into the same environmental niche? One of them's going bye-bye.
Well, I should also mention the Borg is a reference to Star Trek, in case you're not a fan of that or haven't seen it. And that reminds me of one of the Star Trek more recent movies, the Borg. Are they Swedish? Remember that was...
I remember that, yeah. Sounds Swedish.
Anyway, but if you have some really advanced civilization, they're going to know we're here anyways, right? Just from our stray signals that we didn't purposely beam into space. We're just helping them along a little bit by purposely beaming things out.
And the question then is are they looking for these emerging civilizations and wiping them out before they can become a competition?
In fact, we've looked for, and I think this happened a lot, or at least the real beginning of this back in the 1990s, we looked for laser beams, right? Laser light beaming at us. Right. And so there were very rapid pulses of EM waves heading towards us. People had to, look for those, right?
Yep. And they found them.
So that may be, maybe a way. In fact, we're doing that now, right? Did you hear recently there was a test of one of the landers, I think it was on Mars, that they beamed a signal to information by laser beam from an orbiter. Right. So NASA's already, and other countries as well, of course, are already looking at and investing in this type of technology that we're going to beam signals amongst the solar system to different objects using laser light.
Right.
Because it turns out you can pack a heck of a lot of information
Your bandwidth is a lot higher
than for radio photons.
Yes.
And that's just the energy difference there that you're talking about, right? And that energy is proportional to the frequency. So the higher the frequency, like optical light would have compared to radio waves, you can push a lot more information through.
Yes.
So it's much cheaper and easier to transmit that data.
And you can pulse a laser at a much higher energy, what is it, luminance, watts per square meter.
Right.
For a laser is much higher than a beamed radio broadcast.
Yeah, and that's just the energy difference, right?
Right.
And so, yeah, so that's something that will advance for us in the future that's used in laser light. So it makes sense that other civilization may be beaming laser lights in space, really high powerful laser trying to catch people's attention or other life forms' attention.
If I were trying to catch attention, that's how I would do it.
Yeah, and you make it look artificial. So the regular pulses, in fact, pulsars.
And were thought to be signals from extraterrestrials.
Yeah, at first when they thought, some people thought it, but not everybody, of course. And this was back in 67 when they were first discovered. And it turned out to be just natural phenomena, neutron stars rapidly spinning, emitting pulses of radiation. And that's due to the fact that the radiation is beamed on the magnetic poles. And because of the spinning of the neutron star, when that alignment is such that that beam passes us, we see it and then it disappears as the alignment goes away. And then it reappears as it completes the rotation, the neutron star. So you get these pulses almost like the lighthouse effect, right?
I was going to point out that with nearby pulsars like the Crab Nebula pulsar, we're actually finding it does the same thing with visible light. So,
in fact, with things like the Fermi Gamma Ray Space Telescope that's been in space for many years now and others, we discovered that neutron stars beam as pulsars over many wavelengths.
Yeah.
Essentially all of the electromagnetic spectrum. They have gamma ray pulsars, and optical pulsars, and infrared pulsars, and radio pulsars, which is how they were originally formed.
Yeah.
So it's over all different energy scales in that sense, right? So it's amazing when you think about it. So studies of a system like Beta Pictoris may tell us a lot about how solar systems formed in the first place.
Right.
And that'll allow us to target maybe some very interesting stars to see what planets are there and whether possibly we can evidence of life.
how we get these rocks floating in space around stars, how do we get them? This is where we start.
Yeah, exactly. Now, the other thing we wanted to talk about today that's been in the news recently, and this doesn't involve a single star, this actually involves a single galaxy.
Right.
And this galaxy is M87. Now, this galaxy, and you can see three views of it here. On the far left is one taken in radio. In the middle is an optical image or invisible light. And the one on the far right is taken in X-ray. So the interesting thing about this galaxy, first of all, it's about roughly 53.5 million light years away.
Right.
So the star that we looked at, Beta Pic, was on about 63.4 light years away. This object is about 53.5 million light years away. So it is way, way beyond our galaxy, beyond our local group, our collection of nearby galaxies. So it's, it would take you 53.5 million years to get there if you traveled at the speed of light.
Yeah.
So you're talking a long distance away. Now, the interesting thing about this galaxy, when people first started imaging this galaxy, is seeing this little spike coming out from the center region, which you can clearly see in all three of these images, the radio, the visible, and the X-ray. That turns out to be a jet. And that jet is emanating, that is, it's coming from the very center of this galaxy. And at the very heart of this galaxy, and we'll show this later, not right now, is a black hole, what we would term a supermassive black hole. A black hole that has a mass of billions of times the mass of our sun.
Yep.
It is the combination of material that's in the very vicinity of the edge of this black hole, which we call the event horizon, that's responsible, along with magnetic fields, of emitting this jet. Now, the alignment is such that we see one jet. And what we think happens in most of these cases is there's probably a counter jet, one going in the other direction from the black hole.
Oh,
but
it's
because
hidden
of the
from us.
alignment, it's hidden from us. So the jet is almost point directly towards us, but not quite. It's a little bit sideways. So that's why you see an extent or length to the jet. So it'd be like if you took a pencil and pointed directly at you, you wouldn't see the length of the pencil. You just see the lead or the eraser, depending which end, of course, is pointed towards you.
Right.
And as you change that angle of where it's pointing, you see more and more of the length of the pencil until at some point, let's say it's side on, and you see the whole true length of it.
Mm-hmm.
So that's what's happening in this case. The pencil, the jet, in other words, is not pointed directly at us, but off to the side just a little bit. So allowing us to see, some length to the jet itself. So it's projected, as we would say. But there's a counterjet on the other side of the galaxy that we can't see as far as we know. And I don't know if anyone has imaged that in detail. I can't remember.
I can't recall anybody doing
but
so.
most of these jets would be a dual jet, one going one way, one going the other.
Another problem would be is this is an elliptical galaxy, if I'm remembering correctly, and so you'd be looking through the galaxy to get to see the other jet.
And that's actually easier for an elliptical because they don't have a lot of that interstellar matter in the way.
Right.
If it was a spiral galaxy, it would be very difficult to see.
But it would still blur it.
Yeah, and the other thing is, these galaxies themselves can interact with other galaxies, so they can swallow or cannibalize other low-mass galaxies that's in the vicinity that happen to be orbiting around the main galaxy you see here, and that material eventually can get funneled towards the center of the galaxy. Yep. And if that material makes its way all the way down to the vicinity of the supermassive black hole, it forms these big disk systems, in terms of structure, but much larger in scale, like a solar system
size
nebula type of disk. And as that material spirals around in that disk and gets closer and closer to the black hole in the center, it heats up through gravitational tidal effects.
Right.
And it can emit light. So the light is not coming from the black hole itself. It's coming from material that lies outside of the black hole, outside of what we call the event horizon. The event horizon, you can think of that as a place where it's the region from which we can't see anything happening inside of the black hole. What's really happening is that space has curved in on itself. So any light that could be trapped inside of the black hole, there's no path outside to where the rest of us live, if you like.
Right.
It's forever trapped in that region.
I like the way, when we've discussed this, that you described it as the light can now only move in the direction of time, and a time is pointed towards the center.
Yeah. So there's different ways you can think about this. Another way people always seem to use, which is really not strictly correct, but we'll just go with this one, is the place where the escape velocity reaches the speed of light. So if you're a little bit closer to the center of the black hole than the event horizon, you'd have to be traveling faster than the speed of light to get away, which nothing can do, not even light itself. So it's a point of no return.
Yep.
Put it that way. So the light that we're seeing that's part of this jet, it's emitted from outside of that region, from further away from the black hole than this point of no return. So it can escape to the outside universe, which some of that light, of course, we can see with our telescopes.
Mm-hmm.
Okay. So this is evidence, and always have been, ever since we understood these jets' formation and where they come from, is that there must be a supermassive black hole with an accretion disk, as we would say, near the very center of this type of galaxy. So one of the things that was done a couple of years back, and I think the result came out first in, you can see the observation in 2017 here, but it was on that time when the first information came out of the observation of the very first black hole in the center of any galaxy, and this was the one in M87. A couple of years later, I believe, we released the data for this supermassive black hole that's in the center of our own home galaxy, the Milky Way.
Right.
So this particular galaxy, M87, you can see on the left side, that's the image that was released in April of 2017. And this was done by the Event Horizon Telescope, which is a collection of radio telescopes spread around the world, essentially, including in Mexico, including down in Antarctica. It was Chile. There were observations done in the United States and over in Europe, like I believe in Germany, and I think one in Spain as well. Okay. And now they have another telescope in Greenland that they've added to the system. The idea is you spread your telescopes around the Earth, and that one half of the Earth faces a particular target, like this galaxy. And you can collect the signal in radio astronomy that we call interferometry.
Interferometry, right.
We can collect the signal from all the radio telescopes, combine it together, correlate it, as we say, so that the Earth essentially acts like one giant radio telescope in terms of resolution.
Right.
In terms of resolution. It doesn't operate like one giant radio telescope in terms of light gathering power, the ability to collect photons per second, let's say, but in terms of resolution, it does.
Mm-hmm.
So it's a really nifty trick to get very detailed, high resolution of objects that a single radio telescope would not provide, but the combination of signals from multiple radio telescope yields.
Right.
So the image on the left, it was the best we could do at that time in April of 2017, and we barely resolved what's called the shadow of the black hole. The light that you see around the ring-like structure is the light that's emitted from material that's outside of the event horizon of this black hole. So what you see is a darker region in the middle. That's where some areas of the light then is absent, because that's the event horizon of the telescope. And so really it is like the shadow of the black hole. In fact, it's not completely dark. Why? Because some of the material lies in front of the black hole relative to us, and that emits light in our direction. Plus there is lots of gravitational lensing effect occurring here because of that, lots of curvature of space at the black hole itself. So you can even see some of the lights from the disk that lies on the other side of the black hole.
From the back of it.
Gets bent. It's almost like if you watch the movie Interstellar, and I'm not promoting it, but if you ever have time, watch the movie Interstellar. There was great work that was done, visual artwork, and all sort of supervised by Kep Thorne, who is a person that studies general relativity for a living. And in fact, he won the Nobel Prize in Physics for helping with the detection of the gravitational waves a few years ago.
Right.
But anyways, in that movie Interstellar, you see a black hole with the accretion disk that's outside the event horizon. And it's a great, sort of real stunning kind of view. And that's what we expected in terms of real physics at the time, tracing light and what are the various paths it would go in this highly curved space-time environment. Anyways, the thing that's new about this image is that they release data. It takes a lot of heavy-duty processing. In fact, you're talking months to even years of processing this data to correlate all these signals and to get it right. So what you're looking at on the right side is data that was taken about a year later. So that data was analyzed and then released. And one of the things we notice is, number one, it looks almost the same as the image that was taken from data a year prior. Right. That's a good thing, because as we talked about already, like the case with Beta Pic, there are artifacts from our methods and techniques that we use to observe things. Sometimes you don't know if those artifacts are real or not.
Right.
And one way to tell if these artifacts that we're seeing on the image from 2017, if they're real, is in the processed data that was taken, let's say a year ago. So 2018, a year after the 2017 data. So a year later would be 2018. Process that data and see if it looks similar to what you see in the year prior with that data set. And it does look similar. You see the shadow of the black hole. But the other thing you see is changes in where the blobs of light are in that ring-like structure. Why? Because the material that's emitting a light around these black holes is not stationary. It's in rapid motion around the black hole itself. And don't forget, this material is inspiraling towards the black holes on unstable orbits, and a lot of that material is going to fall into the black hole, and eventually, if you can't replenish that material, it runs out.
And some of it gets blown out as jets.
Yeah, exactly. And so we'd expect to see changes in the emission of light in the ring, and that's exactly what we see here. In fact, you can calculate what you would expect based on certain modeling, and it all matches to what you'd expect if there was indeed a supermassive black hole at the center of M87, and that outside of the black hole you have this accretion disk of material.
Right. Remember, we like making predictions and then observing if our predictions are correct. So that's what was done.
Now, it's interesting also to note, if you think about the jet itself, if you want to go back up one slide to remind us what the jet looks like, how a jet forms in the first place. Do jets occur for all conditions where you have a supermassive black hole and accretion disk? And the answer there is no. They don't. Why don't they? Why do certain arrangements of these supermassive black holes with accretion disks, why do they give rise to jets?
I know it has to do with angular momentum, but it also has to do with magnetic fields.
Right, and people don't know the answer to this. It's something people are working on. It's an area in astrophysics that people are trying to uncover. It has something to do with the collimation of collimation of the jet material that is coming in a sort of a pencil beam-like fashion. It's not spread out everywhere. That's related to the twisting of the magnetic fields that are in this highly ionized plasma, this gas that makes up the accretion disk. So those magnetic fields somehow interact with the material in such a way that these jets get launched at some point in the formation of this accretion disk around the supermassive black hole.
And from the X-ray image, I'll just point that out. We know that lumps like the size of Jupiter are being launched at speeds close to the speed of light. So that's why it's emitting in X-rays. Is it's very hot and moving very fast, and it's charged.
So our whole science, this sub-branch of trying to figure out how these jets are created in the first place, that there's a lot of work that needs to be done there.
Yes.
So we should never get the notion that somehow science has discovered everything and there's not really nothing left to do.
You mean like they did at the turn of the 20th century?
Before quantum mechanics was discovered,
right.
And got into relativity effects.
People are actually telling young students not to get into physics. We know everything at the end of the 1800s. We know everything. It's just putting the icing on the cake.
Yeah, and making more precise measurements. In other words, dotting the I's and crossing the T's. And that turned out to be a whole revolution that occurred shortly thereafter.
Yep.
When you think of relativity and then quantum mechanics that followed after that. So anyways, I think that's it. We're running out of time for today. So if you're interested in maybe trying to explore ways of figuring out how jets get launched for these AGNs, these active galactic nuclei, as we call them, black holes, accretion disks, these sort of things, one way to do that, of course, is to go to higher education, higher learning experience. So learn more about math, learn more about physics, become a scientist, get into whatever field that you feel like you have motivation to study, whether it is physics or biology or anything else. We need lots of people working in these fields. When is the new cancer drug going to come out that will revolutionize treatment of cancer? How does life form to begin with? How do these jets form these AGNs? What's this about dark matter and dark energy? There's so many wonderful puzzles out there. I wish I could do my career over and over and over again and tackle some of these issues. It's amazing when you think about it.
There's always something more to learn, as Wondergoon says.
Yeah, and so you can start your study, if you like, by attending classes both online and in person at the University of North Dakota. So we would appreciate it if you could do that. And if you are around on campus and you listen to this podcast, feel free to talk to us.
Come join us. Come see us. We like that.
Now, the next podcast will be Tuesday, January the 30th. Mm-hmm. So this will be at 3 p.m.
Almost the end of January. Wow.
Almost the end of January. And we always leave you with a quote at the end. Mm-hmm. So fittingly, this quote is related to black holes.
Black holes. Woo.
So the quote is actually from John Wheeler, who was a very prominent scientist at Princeton University. So here's his quote. "The black hole teaches us that space can be crumpled like a piece of paper into an infinitesimal dot, that time can be extinguished like a blown-out flame, and that the laws of physics that we regard as sacred, as immutable, are anything but."
They can come to an end.
Thank you very much for watching and listening. Don't forget to give us a like on our podcast, subscribe if you haven't done so, and we'll see you next week.
See you next week, folks.